Okay, so last time we started talking about or really delved into the next sort of big class of reactions, which are really our redox reactions. And our redox reactions, if you remember, basically means oxidation and reduction. And they always occur together. So if something is being oxidized, there is something that is being reduced. There were several definitions of each of these, but really in sort of general chemistry, we come across oxidation in terms of losing electrons, and reduction means gaining electrons. And typically, when you lose electrons, as we've talked about, you do become more positive, and if you gain electrons, obviously you become more negative as you have extra electrons. And that sort of simple explanation of oxidation reduction, along with what we kind of talked about, you could kind of just use a simple sort of number line to help you figure out, is something being oxidized, is something being reduced. Again, if you become more positive or moving in sort of that more positive direction, then you are going through oxidation. Again, you're losing electrons, basically have more protons than electrons, more positive, and you're going through oxidation. If something gains electrons, again, becoming more negative. So if you kind of move along the number line towards the more negative side, that is something that is going through reduction. So by simply just really following the change in the oxidation state from the reactant side to the product side, just simply put it on the number line and move it one way or the other. It's a very sort of simple, almost foolproof way of correctly identifying what is being oxidized and what is being reduced. In addition, we also talked about the idea that there are what are known as oxidizing agents and reducing agents. And remember that when we talk about the oxidizing agents or reducing agents, they are pretty much opposite of the name. So the substance that is the oxidizing agent is actually the species that is being reduced. And the guy that is the reducing agent is the species that is being oxidized. And the reason they're called, sort of the oxidizing agent or reducing agent is just because of that. Again, the oxidizing agent has to cause the substance to get oxidized and lose electrons in order for it to basically gain the electrons and become reduced. While the reducing agent is the substance that basically gives away its electrons and allows something to basically be reduced, and that would means that it's going through oxidation. So the easy way to remember it is, again, if you're sort of asked about the agents, it's the opposite of the name. um, the other nice thing is, as we talked about, that both of these things again do happen together, which means if you're perhaps only able to identify what is being oxidized, by default, the other sort of substance there would be going through reduction. So it's sort of a process of elimination sort of situation, and you can sort of easily determine that. Now, when we talk about redox reactions, these guys really are sort of like the big umbrella of reactions, like we were talking about earlier in this chapter about double displacement reactions being sort of also a big umbrella of reactions that are taking place. Remember that underneath sort of that double displacement umbrella that we talked about earlier on in this chapter, we had things like our precipitation reactions, we had our acid base reactions. And so these are, again, other ways that you could classify, a type of reaction, but, sort of ultimately what's happening is a double displacement reaction in those cases. And we have these more sort of specific classifications as we go down. We're going to see the same thing here with our redox reactions. Again, it's really more of a big umbrella for which we'll see some other types of classifications that occur, things like synthesis reactions, things like decomposition reactions. things like single replacement reactions. So these are, again, a bunch of reactions that are ultimately really redox reactions, as we'll talk about, but also, again, can be classified in a more specific way based on some type of object that you're looking at. When we talk about the oxidizing agent and the reducing agent as well, just a reminder, that is found on the reactant side. Also, when we write half reactions, so for example, this would be considered the oxidation half reaction because electrons are being on the product side here. They're being like they are given off or lost. While if we have more of a reduction half reaction, it would look something like this, where we see electrons in the half reaction on the reactant side like they are being gained. Remember that these are called half reactions because when you basically add them together, you get the overall reaction that's basically taking place in this particular example here. So when we do add these back together, one important thing, as we talked about as well, we'll talk a little bit more about as well today, you always want to make sure you have the same number of electrons in each half reaction. The electrons should always be on opposite sides of the arrow. If you ever have two half reactions you're trying to add together that the electrons are on the same side of the arrow, you definitely have made a mistake. Any questions on that stuff we talked about last time? So we saw some examples of some redox reactions last time. And, how do we know, what is changing in terms of the oxidation number? And we do look at oxidation number to help us decide, what is being oxidized, what is being reduced. So let's talk a little bit how you properly assign oxidation numbers. These are also sometimes referred to as oxidation states. And when we talk about oxidation number or oxidation states, it's important to remember, and sometimes it's hard for students, that oftentimes we have in our head sort of the charges, if you will, that something like a nonmetal, for example, has when it's in an ionic compound. And oxidation numbers and oxidation states are not necessarily the same thing as the charge. A lot of times we'll deal with these guys in more covalent sort of situation. So really it's sort of the charge that these elements would have in their sort of arrangement in that particular molecule. So again, a lot of times we will come across things in more of a covalent compound, molecular compound, where electrons are being shared. So when we think about, say, something like nitrogen, for example, we often think of it as like always a -3. And that is true when it is usually hooked up with a metal. But if we have nitrogen in some type of covalent compound, it may actually have more of a positive sort of oxidation state rather than the -3. So when we talk about oxidation states, it's sort of, you can think about it, the charge that the atom would have in that particular compound if all the electrons were transferred. And again, it may not always be the charge we think about when we think about certain elements when they're in ionic compounds. So some of the rules here in terms of applying oxidation numbers, anything that is basically by itself, uncombined, sort of naturally how it comes, will have an oxidation number of 0 or oxidation state of 0. So that's all the metals. So for example, sodium here is sodium metal, like a solid, no charge or anything associated with it. A reminder that metals only get charges when they hook up with like non-metals, for example. So if we have just the metal by itself, it has no charge. Our kind of diatomic guys here, how they naturally come, have a 0 for the oxidation number. If it's a monoatomic ion, the oxidation state will equal the charge on the ion. So if you have something like lithium, which is +1, we'll have a +1 oxidation state. If you had iron 3, like you were dealing with iron 3 chloride here, the iron would be +3 in this particular case. The chloride would be -1 in terms of their oxidation states. Oxygen is a really good place to start. Usually when you're assigning oxidation states or oxidation numbers, are a lot of times dealing with redox reactions. Oxygen is oftentimes found in the situation a lot, and it is -2. So oxygen is usually a very good place to start when you're assigning oxidation numbers, and it's usually -2. There is an exception, and that exception is if it's really not oxygen and it's peroxide. And like in hydrogen peroxide, it's actually -1. And that's because this guy right here is those polyatomic ion, which is peroxide. So you'll have that -1 here for oxygen rather than -2. Again, in something like hydrogen peroxide, you'll be able to sort of note that. Um, I would say probably in most cases when you see oxygen, it's fairly safe to assume that it is going to be -2. But, you know, if you can recognize it obviously as peroxide, it would definitely be -1. In addition, a couple other important sort of rules. Hydrogen is usually +1, except if it sort of comes second in a formula. And usually in that case, it would be following a metal like something like LiH, that's lithium hydride. Here, the lithium would be +1, and the hydrogen here is actually -1 in terms of its oxidation state. Things in group 1 are always going to be +1. They kind of have those fixed charges. +2, fluorine's always going to be -1 as well. When we add up all of the oxidation numbers in a compound, a molecule, or an ion, it needs to equal the charge. So if you're adding up oxidation numbers for something that is neutral, everybody needs to add up to 0. If you're adding up a oxidation states for an ion that has an overall -2 charge, everything needs to add up to -2 when it's all said and done. Although a lot of times we do deal with oxidation numbers that are kind of whole numbers. They don't have to be. So for example, here, superoxide is -1/2. So it is possible to have sort of a fraction, if you will, like a 0.5 in terms of the oxidation state in a particular compound. Other important things when we talk about writing oxidation states or identifying oxidation numbers is you should include the charge. So if something is a -2, you should write -2, not just 2. Something is +2, you should put the plus in there as well. So when you're identifying oxidation states or numbers, you do want to make sure you always include the charges with your oxidation number. Any questions on that one there? All right, so let's take a look at this example here. This is bicarbonate. And usually a fairly good rule of thumb when you're dealing with a ion like this, or maybe a molecule or something like this. And what I mean by like this is it's kind of 3 elements there, especially as there's kind of 3 elements and oxygen's on the one side. Usually it's very good to start with the oxygen. And if we did that, it would be -2 in terms of its oxidation number. And then usually in this case, if you have like a 3-pack of elements here, usually you want to leave the guy in the middle for the end. So kind of go to the other end, and hydrogen in this case would be +1 in its oxidation state. Now, what we're looking for is what would be carbon's oxidation state in this particular ion. Because there's 3 oxygens and each of them are -2 in terms of their oxidation state, that's sort of like a -6 overall charge. We also have the +1 on the other side. Now, when we look at bicarbonate, it has an overall charge of -1, which means when we add up all of our oxidation numbers, it does need to equal -1 when it's all said and done. So quickly looking here and doing this math, that is -6 and +1 is -5. Remember, we want to end up with -1. That means in this case, the carbon should be not +5, but the carbon should be +4, if I read that right. And when we do that, +1 and +4 is +5, -6 is -1, and that would be the oxidation numbers for each of these guys. First off, any questions on how I assign those numbers?
Yes, can you explain how you got +4 again?
Yeah, so what we got going on when we look at these guys, oxygen is -2, and because there's 3 of them, that sort of overall charge, if you add up the oxidation numbers, gives us a grand total of -6. And that's because basically each oxygen is carrying a -2 oxidation state. So -2, -4, -6. Hydrogen is +1, and there's only one. So that gives us a +1 oxidation state for the hydrogen. So if you make it kind of like a math problem here, we're missing the oxidation state of our middle guy, which is carbon in this case, and we could call that X. This entire thing, when you add up the entire oxidation numbers for everybody that's sitting there, it all has to equal -1. That means when we solve for X, if you kind of want to do it in this math way, you basically would be adding 6 over here, right? And that would get you a 5 is equal to X plus 1, basically. And then taking that to the other side would get you X is equal to 4, which would be +4. So just adding it in there, +4 equals -1, because that's what everything needs to add up to. That gives us +1 and +4 is +5. -6 gives us -1, which is how we get to that +4 for the carbon. Other questions? Now, important how you sort of write the answer, because it's very common people will screw this part up as well. When you're asked a question like this, the hydrogen oxidation state should be +1, again with the charge. The carbon's oxidation state should be +4, again with the charge. And oxygen's oxidation state should be -2, again with the charge. And what I mean by -2 is that is the proper oxidation state for oxygen here. It is not -6, which is the grand total of all of them individually added together. So sometimes people will go -6 for oxygen because that's like the grand total. So when you're asked to sort of give the oxidation number, it has to have the charge, but it really is if you just took one of the elements out by themselves and what the charge is on that particular guy by itself. Any questions on that there? Okay, so why don't you try a few here, see what you end up with. Actually, we'll take a look at this first. So here's some oxidation numbers of some common guys here on the periodic table. And again, you can see where I talked about nitrogen a minute ago. You can see it has a wide variety of oxidation states, all the way to +5 to -3. You can see chlorine as well, which oftentimes gets people. Chlorine can even get up to +7 in certain situations. Or Mn has a lot of them as well. But a lot of times, some of these guys we're used to, especially on the metal side, there are a lot of the sort of normal charges that we're familiar with. But again, when we're talking about non-metals, sometimes that confuses people because we think about ionic bonding and we think, oh, wait, phosphorus should always be -3 no matter what the situation. And that's probably true in an ionic compound. But again, if we're dealing with something that's more molecular, covalently bonding, that phosphorus may actually have like a +5 sort of charge. Same thing with like our bromine and so forth coming through here. So just keep that in mind. Again, if you're looking at sort of an ionic compound, it will probably be identical to sort of, I should put it this way, if you're looking at a binary ionic compound, which means 2 elements, basically a metal and a non-metal, they will have the charge on those guys will be their oxidation numbers. But if you're dealing with something that has any type of covalent bonding involved, you're going to get some numbers that are maybe different than what you might expect for certain things. So now why don't you try for these guys here? Why don't you see what you come up with? So for each of these, give the oxidation numbers for each of the elements and take a minute or two and see what you come up with. Okay, so let's take a look and see how we're doing. We'll start with the guy on the bottom. So again, in this sort of 3-element situation, again, usually start with the oxygen, go to the other side, leaving the guy in the middle, alone till the end. So starting over here, oxygen would be -2. There are 3 of them, which gives it a kind of overall charge there of -6. Going to the other side, we have sodium, which is group 1, which means it's +1. Now, this entire thing here, sodium iodate, is neutral, basically has no charge. So when we add up all these numbers, it does need to equal 0. So if we just kind of add up our total at this point, we got -6 and +1. That gives us a -5 overall. That means to balance it out here, the iodide would be carrying a +5 charge. So our sodium would be +1. Our iodide would be +5, and our oxygen here again would be -2. Any questions on that there? And that's why, something like IO3 minus has a -1 charge because the oxygen is -2. And there's 3 of them, which gives you -6. The iodide here is +5. +5 and -6 equals -1, which is really the charge on that polyatomic ion is -1 because the iodide here, unlike we normally think of iodide as carrying a -1 charge, actually in this arrangement, because it's actually sharing electrons here between these guys, is carrying a more +5 sort of configuration. Any questions on that there? Coming up to the top here, our fluorine is always going to be -1. And since there's 7 of them, that gives us a -7 for kind of the fluorine side. Again, here, this entire thing has no charge, which means when we add that up, it does need to equal 0. That would mean that the iodine here is now carrying a +7 charge, different than what it is carrying in this configuration. Here, attached to 7 fluorines, the iodine is going to carry a more +7 charge to balance that out to 0, right? -7. And that means again that the iodide would be +7, fluorine would be -1 in terms of its oxidation numbers. Any questions on that there?
Could you explain that one more time, how the numbers switch with that?
How we got to the +7 for the iodine? Is that what you're asking? Or
Yeah.
yeah. So again, in this situation, the thing is neutral, which means it does need to add up basically to 0 overall charge. Because fluorine has always sort of an oxidation number of -1, and there's 7 of them, so each one's basically carrying like a -1 charge. For the fluorine side of the molecule, it's carrying kind of a -7 charge. Because the entire molecule is basically neutral and equal to 0, to balance that out, we do need a +7 on the iodide side of the molecule. So iodide there would be carrying a +7 plus -7. It's basically 7 minus 7 gives us the 0 charge that's happening in this case. And that's different than in, say, this one we were just talking about here, because there's actually 3 oxygens that are involved. The iodine actually only needs to carry a +5 situation in that case. And again, the oxidation state really is not necessarily the sort of charge that we associate with certain elements in their ionic form here, but because in their sort of molecular sharing of electrons with electronegativity, they're going to carry on a different sort of oxidation number than they may in an ionic compound. Because in an ionic compound, they're going to have a complete transfer of electrons. So those electrons are going to be completely transferred and not really going to hang on to them. So they pick up the entire electron. And something like IF7, really badly drawn one here, we'll just kind of scribble it around. Think about sort of what is happening here. I think I may have missing one there. One more, we'll squeeze one in, sort of this deal, right? In theory, what's happening, right, is you have all these fluorines, right, which are incredibly electronegative. And what does that mean? What that means is in this configuration with that really strongly electronegative fluorine, all the electrons that are being shared by the iodine, they're all going to be really heading kind of towards the fluorine, right? And what is that going to kind of be doing to the fluorine in this situation? It's going to make it more and more electron deficient. Did it lose those electrons? It didn't, but it's almost like it lost those electrons. And that's why it gets this really big positive charge in this sort of orientation, as opposed to when we hook it up over here with the oxygen. I won't draw it correctly, but we'll just kind of do this sort of move here. Again, the oxygen here is more electronegative, but there's kind of only 3 of them. And again, they're going to be pulling those electrons away from the iodide in this particular case. And in this particular case, what's going to happen is the iodine again is going to become more electron deficient to a part where it becomes almost like it's carrying a positive 5 charge, almost like it's lost now 5 electrons, even though it technically hasn't because it's sharing electrons, but it's becoming more and more electron deficient. And that's different than when we deal with something like, say, sodium iodide, right? In sodium iodide, this guy's going to be +1, this guy's going to be -1, which is what we normally think about in terms of iodide, in terms of like a charge. The difference here is because this is a metal, non-metal, we're going to get that electron completely transferred from the sodium to the iodide, which is why it carries that -1 charge, because there's a different sort of bonding happening in an ionic compound. We're getting an actual transferring of electrons. And because nonmetals are more electronegative than metals in an ionic compound, what typically happens is those electrons are now transferred over to the nonmetal completely, and it typically gains that more negative charge. But when we kind of hook up sort of nonmetals together, we oftentimes will get some more positive situations happening, because like the iodine in the middle with the fluorine, it's just getting all its electrons really pulled away from itself and becoming more and more positive because of that, even though it hasn't necessarily transferred those electrons. And the same things happen with the iodine and the oxygen, again, kind of pulling those electrons apart. Other questions on that? All right, so looking over here, we have potassium dichromate. Again, the situation, we want to kind of look at it in terms of the oxygen first, which will be -2. And again, going to the other side, we're going to go to our potassium, which is +1. And in this situation, we got a couple of different things happening. We got 7 oxygens in this case. Each of them at a -2 oxidation state gives us like a -14. We have 2 potassiums at +1, gives us a +2. Again, here, this is a neutral guy. This is a dichromate, which is one of those polyatomic ions. And in this particular case, though, the difference is we don't have just 1 chromium hanging out there. We actually have 2, right? And in this particular case, that means we got to kind of figure out what that each one would be. So plus 2 and minus 14 gives us a minus 12 overall. Because there's 2 chromiums, you kind of just divide it by 2. That means that we get up with a minus 6, but to balance it out, it does need to be plus 6 in this case, right? So 2 times plus 6 gives us a plus 12. Plus 2 plus 12 is plus 14. Minus 14 is 0. So in this particular case, the oxygen carries a minus 2 oxidation state. Potassium carries plus 1. And chromium would carry a plus 6 oxidation state. Again, those would be the oxidation numbers we would want to kind of put together. Any questions on that there? Okay. So it is really important, especially when we're dealing with oxidation numbers, to make sure that you understand how to apply those correctly, because it's going to help you, especially when we talk about balancing redox reactions, understand what's happening, what's being oxidized, what's being reduced. All right, let me continue on. And now that we sort of have an idea as to sort of how to assign these oxidation numbers, let's now look at some different types of redox reactions. And again, as I mentioned before, we're going to be able to really classify these reactions in a couple different ways, but ultimately they are going to be sort of redox reactions that are happening. The first one is a combination reaction. This is also sometimes referred to as a synthesis reaction. So combination or synthesis, I'll spit that out. And really in a combination or synthesis reaction, much like it shows here, basically we put 2 things together to make one thing. So you basically 2 things make one thing is the general sort of setup that's happening here. Now, if we take something like, say, aluminum and bromine to make aluminum bromide, we are having 2 things make one thing. So that's your classic combination or synthesis reaction that's taking place. This is also, as I mentioned earlier, a redox reaction. So if we look at this, we have aluminum by itself, which means it has a 0 oxidation state. Br2 is naturally how bromine comes, uncombined, also going to have a 0 oxidation state. It's not until we get this ionic compound that really aluminum gains a charge and bromine gains a charge. And aluminum in this configuration is +3 and bromine is -1. So if we think about our little sort of number line, if you will, if we look at the aluminum is starting at 0 and heading towards +3, which is in this direction, right? And going more positive means that the aluminum is going through oxidation. We could do the exact same thing for the bromine. Bromine is starting at 0. It is ending at -1, which means the bromine is traveling in this direction, becoming more negative. And when you become more negative, that means you are going through reduction in this case. And again, that's a very simple way to figure out oxidation and reduction. In this case, the aluminum, which is going through oxidation, would be our reducing agent. The bromine that is going through reduction would be our oxidizing agent. Again, reducing agent, oxidizing agent found on the reactant side. Question on any of that there? Now, although we can classify this as a redox reaction, most people would probably look at this and classify it as a combination or synthesis reaction. Again, remembering the redox reaction is the big umbrella, and kind of underneath that is this type of reaction, which is a combination reaction. Now, another type of redox reaction is a decomposition reaction, which is essentially the opposite of this reaction we just talked about. So combination or synthesis, you put two things together to make one thing. Decomposition reaction, you take one thing and you break it apart into, two or more things that are happening here. So they're kind of opposites of each other. Synthesis, put it together. Decomposition, break it apart. And that's what we see here when we look at potassium chlorate, and it breaks apart into potassium chloride and oxygen. So again here, this is a classic decomposition reaction. We got our one thing into two things. You may not recognize it, but again, it is a redox reaction that's happening. So let's take a look at our oxidation numbers here and see what we end up with. Starting here at the oxygen on the right, that's going to be -2. That's -6 for the oxygen. Potassium will be +1. So -6 and +1. And this overall thing has no charge, means that the chlorine here actually is carrying an oxidation number of +5 in this particular case. +5 and +1 is +6, and -6 is 0. Coming to the right-hand side, potassium is +1 since this is an ionic compound. Chloride is -1 since this is an ionic compound. And oxygen is 0. So we got a lot of elements here. We actually have 3 different elements. Let's see if we can figure out what is happening with each of them. Again, if you want to use the number line to help you, we will start with the chlorine. So the chlorine is actually starting at +5. So that would be like over here. It is ending at -1, which means the chlorine is heading in this direction, right? And going in that direction means you are going through reduction here, the chlorine. Let's take a look at the oxygen. The oxygen started at -2, which is over here, ending at 0, which means it is moving in this direction, becoming more positive, which means it is going through the oxidation, the oxygen. Now you maybe ask yourself, what about the potassium? Well, potassium started at +1 and ended at +1. Nothing changed with the potassium. It's really just a spectator ion here. Nothing's happening to it. It's just kind of hanging out. So there's really no change that's occurring with the potassium, and that does happen in this particular case. So in this particular case, again, the chlorine is going through reduction. The oxidation is happening on the oxygen, and really the Cl here is our oxidizing agent, and the O is our reducing agent in this particular case. Any questions on that? So this is, again, a redox reaction, but most people would classify it as a decomposition reaction. We've seen decomposition reactions as well. We saw a little bit earlier when we were talking about gas producing reactions and double displacement. When we produce something like carbonic acid, if you remember, that will decompose very quickly into water and CO2 gas. And again, one thing making two things on the right-hand side. Again, your classic decomposition reaction. All right. So these are two different classifications of reactions. Also, again, over that big umbrella of redox reactions that are occurring. Another type of sort of redox reaction is one that's referred to as a combustion reaction. And there's kind of two definitions of combustion reactions are different definitions depending on sort of what you're looking at. So your basic general definition of a combustion reaction is essentially you just need oxygen, basically there. So if you technically have a reaction that involves oxygen, it technically is a combustion reaction. Now, most people, when they think about a combustion reaction, think about the organic combustion reaction. And that's when you take an organic compound That's basically carbons, hydrogens, oxygens, plus our O2, making CO2 plus some water. And that obviously makes heat and flame and stuff like that, like methane, propane, butane, all those kind of things. So for example, like CH4 plus some O2 makes CO2 plus some water. And although, we don't think about this as, this is usually the one we think about in terms of a combustion reaction. Technically speaking, you don't need those elements. You really just need the O2 technically being present. And you may say to yourself, well, is this a little balancing, I suppose, is the right thing to do. Is this an oxidation reduction reaction that's taking place? Well, actually, yeah, it is. The carbon here is actually gaining oxygen as it goes this way, which is another definition of oxidation. And the oxygen is gaining hydrogen, which is a definition of reduction. So most of the time we think about more of the organic reaction as the combustion reaction, but basically, like I just mentioned, you pretty much just need oxygen involved. So this would be classified, this could be classified as an oxidation or a combustion reaction here. Oxidation stays 0 and 0. In this situation, oxygen is -2. There's -2 and times 2 is -4, which means oxidation state here of the sulfur is +4. Again, if we're trying to see what is happening with each of these, taking the sulfur starting at 0, ending at +4 means it is becoming more positive and going through oxidation. Looking at the oxygen starting at 0 and ending at -2 is going through reduction. So again, it meets our definition of redox as well, also known as a combustion reaction. And you might even look at this and go, isn't this two things that make one thing? And you would be correct. Some people might even call this a, very rightfully so, synthesis reaction, right? That's basically two things that make one thing. So you're probably starting to see a trend where, you can have multiple classifications for the same reaction depending on sort of what you're looking at. This is the same thing here. Most people might call this a two thing makes one thing situation, and it can be rightfully classified as a synthesis reaction as well. Because it has the O2 involved, it can be classified as a combustion reaction as well. And in case we're missing any other type of classification, we have a 0 oxidation state here, a 0 oxidation state here. Oxygen is -2 and magnesium is +2. And again, don't want to ruin the ending here, but this will also be classified as a redox reaction. If we look at magnesium starting at 0, ending at +2, going through oxidation. If we look at oxygen starting at 0, ending at -2, going through reduction. And that's basically your metal, non-metal happening here, right? Transfer of electrons, right? And so this one reaction on the bottom, even the one in the middle, you could classify 3 different ways, really. You could call it a combustion reaction. You could call it a synthesis or combination reaction, or you could classify as a redox reaction. Probably in most cases, people would classify this one, probably both of these, more in the vein of combination or synthesis reaction. But again, you could have some of these cross classifications as we've been talking about. Any questions on that? Here. Now, another really sort of big category of redox reactions is a single replacement reaction. So we've seen single replacement reactions a couple of ways, but single replacement reactions have the general kind of setup of A plus BC And we talked about it a number of times, I think, in lab as well. This is something with no charge, but this is like an ionic compound. And if this happened to be a metal, it would come in and kick out the positive guy, and it would make a new ionic compound. And that positive guy would come out with no charge in this situation. We could also have this reaction where the first guy is a non-metal. And we saw that way back when on one of the very first labs that we did, when we did those halogens. And this guy then would kick out the non-metal part of that, which is the negative guy, and make a new ionic compound. But this guy would come out with no charge. Remember that in order for whatever is coming in to actually make this reaction occur, whatever is coming in needs to be more reactive than what it replaces. So whatever coming in needs to be more reactive than what it replaces. If it's not, then that reaction will not take place, and it will not actually take place, and you'll get actually no reaction that takes place. Now, even though we got sort of this sub-classification happening here, again, big umbrella redox, kind of underneath that umbrella, single replacement reactions. You could even get very, very specific about what is happening in terms of the replacement, or sometimes referred to as displacement. Here, if we look at this guy here, we have basically a metal that has a 0 oxidation state. Oxygen is -2, hydrogen is +1. This guy is going to come in and kick out the hydrogen. When hydrogen gets kicked out and it becomes hydrogen by itself, uncombined, it becomes H2 gas, right? That's the natural way hydrogen is. And you would see bubbles kind of happening as a result of this reaction. What is happening on the back end here in terms of our states? Well, strontium now becomes a +2 in this situation. Hydrogen becomes a 0. And what we get here is what is sometimes referred to as a hydrogen displacement reaction, basically because we're kicking out hydrogen. What is happening in terms of oxidation reduction? Well, strontium is going from 0 to +2, so it's going through oxidation, which means that this would be our reducing agent in this case. And it's actually the hydrogen here going from +1 to 0, which is going through reduction, which means that it is the hydrogen here. And that means that the hydrogen over here, or the water in this case, would be our oxidizing agent. Any questions on that there? Here's another example, but this is what is sometimes referred to as a metal displacement. Same situation. This guy is positive. This guy is negative. This has no charge. He's going to come in and kick out the positive guy, resulting in the guy getting kicked out, coming out by itself, and some guys over here. What's happening with our oxidation states? Well, chlorine is -1 in this ionic compound. That's going to be a -4, which means the Ti is +4. How did I know the Cl here was -1? It's because this is an ionic compound. So again, in an ionic compound, Cl will carry the oxidation state that we normally think about for Cl, which would be -1. Magnesium is by itself, which is 0. When the Ti now comes out as the metal by itself, it now has a 0 oxidation state. Magnesium hooked up with the chlorine +1 and -1. So again, if we look at what is happening there, and we look at the Ti, it is going from +4 to 0, which means it is going through reduction, the Ti. If we look at the magnesium, it's starting at 0, and going to +2, which means it is going through oxidation. What is happening with our chlorine is -1 on the left and -1 on the right. Nothing is happening with our chlorine, so no change occurring there. Really, chlorine would be considered a spectator ion here, and it would actually cancel out if you went through and did like a net ionic equation that's happening. This again is what is referred to as a metal displacement, because a metal is coming in and kicking out another metal. Another type of displacement is one that we actually saw in that experiment that we talked about just a second ago, and that's a halogen displacement. And that's because group 7's involved. What's happening here is this guy is going to come in and kick out the other halogen that is present. Chlorine all by itself, not attached to anything, zero oxidation state. This is an ionic compound between potassium and bromide, and that means that bromine will have a -1 charge like normal. Potassium will have a +1 charge like normal. KCl, that also is an ionic compound, which means the chlorine here will carry the normal oxidation state for it. Potassium will be +1, and bromine will end up being 0 on the back end. Again, if we take a peek at the little number line there and look at our chlorine starting at 0, ending at -1, going to the left or more negative, going through reduction. And our bromine in this case starting at -1, ending at 0, moving in that direction there, but going through oxidation. And that means that our bromine is going through oxidation. That means that, let's see, chlorine was going through reduction. That is our oxidizing agent. And that would make this our reducing agent in that case. And by the way, for the Ti and the magnesium is getting oxidized, which means it's the reducing agent. The TiCl4 there would be our oxidizing agent. So each of these technically are really redox reactions happening. They're really usually probably classified under the umbrella of single replacement reactions, even though they do fall under the big umbrella of redox reactions. Question on any of that there? So how do you know if this reaction is going to take place? As we talked about, in order for this reaction to take place, basically whatever is coming in does need to be more reactive than what is replacing. So, you know, there's what is referred to sometimes as an activity series of metal. And your basic activity series of metals, you sort of made one in that sort of experiment we're talking about. You know, the basic activity series is kind of just a list of elements, and somewhere in the middle there's hydrogen and some more elements. And basically anything higher on the list is more reactive than anything lower on the list. And what that means is if you look at the list, anything that's higher on the list should replace anybody lower on the list, and vice versa. It would not necessarily happen, you know, in that opposite sort of arrangement. So here's a more detailed sort of activity series, but if you kind of just kind of look at the left-hand side, it's kind of like your basic activity series per se. You know, you got kind of your hydrogen, and then you got kind of above it some guys and below it. So, you know, if you look at something, say like zinc and hydrochloric acid, right? We're talking about the zinc trying to replace the hydrogen. The zinc is higher on the list than hydrogen. Where'd it go? So we would expect that reaction to take place. But if you swap it out for like copper for your hydrogen, replacing your hydrogen, copper is actually lower than hydrogen. We would not expect that to happen, and this reaction would not take place. So an activity series can be very helpful in kind of helping you determine whether or not a reaction would take place. This again on the left here is a very detailed sort of reaction or explanation. So if we look at something like this, if we have this available to us here, calcium, hydrogen, again, we're looking at calcium trying to replace hydrogen. here is calcium. It reacts with cold water, and that pretty much means that's all you need in that situation. This reaction would take place because of that. Now, if we look at lead coming in to kick out the hydrogen, if we find lead up here, lead is over here, it actually needs an acid to make this reaction occur. Water is not sufficient enough to have a sufficient amount of really H in the solution to allow this reaction to take place. So this second reaction actually would not take place because of that. Because in order for that reaction to take place, you would actually need to react it with an acid like hydrochloric acid. So it does depend on whether you're trying to use water as your source of hydrogen or your acid as your source of hydrogen. And this is why I think in the lab, we talked about it the other day, sometimes water is written like this, kind of like an acid. You know, this is sort of thinking water as a source of H+. And again, sometimes this is sufficient source of H+ to allow this reaction to take place. And sometimes you need something that really will provide a little bit more in terms of hydrogen for that reaction to take place. Any questions on that there? Now, in that experiment, we saw that in terms of the halogens, really group 7 on the periodic table is our activity series for our halogens. So if you remember from that experiment, I almost want to say it's experiment 4 or 3, one of those. We remember in terms of reactivity, right? Reactivity increased as you went up this group, right? And what that means is, you know, if chlorine's coming in to replace bromine, that will definitely occur. That's good. If bromine wants to come in and replace chlorine, that's not going to occur. Again, bromine being lower on the period there, going to be less reactive than chlorine, but chlorine would come in and kick out bromine, which is exactly what we see here. The chlorine is coming in to kick out the bromine. That should happen. That's this move right here. This reaction should take place. Also, again, a redox reaction, that's 0. That's +1 in terms of its oxidation state. That's -1. Again, bromine being -1 here because it's an ionic compound. On the other side, +1 for potassium, also -1 for the chlorine because it's an ionic compound. Bromine by itself, 0. So here we see chlorine going from 0 to -1, heading in that direction, going through reduction. And we see the bromine starting at -1 and ending at 0, going through oxidation. And so this reaction would take place. Now, if we tried to do the second reaction, which is iodine replacing bromine, if we look at the list, basically iodine would want to replace bromine. Iodine is lower on our list there, or group 7, means it's less reactive than bromine. So this reaction would not take place because of that. It is less reactive. And basically you would get no reaction here. Question on single replacement reactions, which are again basically redox reactions that are happening here. Any questions on any of that there? Now, speaking of sort of redox reactions, there's actually some type of redox reaction, which is what is referred to as a disproportionation reaction. That is a big word that means the exact same element in a particular reaction is both being oxidized and being reduced at the same time. So it's like the same element going through both things, being oxidized and reduced at the exact same time. And that's what we see here a lot of times in sort of chlorine chemistry. We have a lot of that happening. And what we see here is the chlorine here is 0. The chlorine in this first guy, the oxygen is -2. There is a -1 charge. So the oxidation state of the chlorine in the that is hypochlorite, is +1. The chlorine over here in chloride, like an ionic compound, is -1. And again, you may be wondering about your oxygen and hydrogen. This is -2 +1. This is +1 -2. So when we think about oxygen, nothing is happening. When we think about hydrogen, nothing is happening either. It really is the chlorine. And in the chlorine, in one case, is starting at 0 and ending at +1, which is going through the oxidation. Now that same chlorine is starting at 0 and ending at -1 in the other situation and going through reduction. This is what is known as, again, a disproportionation reaction. The exact same element is both being oxidized and reduced in the same reaction. Any questions on that? Now you may ask yourself, what would my two sort of half reactions look like? Well, it would both start with chlorine. Your 1/2 reaction would look something like this. And again, in this situation, it is going from 0 to -1. It is losing electrons, which means you would end up with electrons on this side. Then you would start with the chlorine, the Cl2, going to the Cl-. In this case, it is gaining some electrons, right? So it's gaining some electrons over here. I didn't balance it, obviously. But, this is what sort of your two half reactions would look like. Again, both starting with chlorine. The difference is they're ending at sort of different products, and each of those different products carry a different oxidation number for chlorine. Any questions on that there? So just a few different ways that we could kind of classify these reactions. As we've talked about, there's a number of different ways to classify even the same type of reaction. It does depend on sort of what you're looking at. So in most cases, people will sort of try to classify them, based on one aspect or the other. People oftentimes kind of do, I would say a lot of times in general chemistry per se, the classification doesn't necessarily always redox. So a lot of times the redox aspect of it is usually kind of classified as either a synthesis, a combination, a combustion, a single replacement reaction. Well, I will say sometimes, a lot of times, the double displacement sort of classification, a lot of times those guys are classified as double displacement reactions rather than, say, a precipitation reaction or an acid sort of base reaction. So it's kind of an interesting two umbrella approach. Oftentimes people will go more with the double displacement classification rather than the more specific acid and base or precipitation reaction. While on the redox side, a lot of people will avoid the redox part of it and go with the more synthesis, decomposition, single replacement, more classifications. So again, you can classify these guys as a multitude of ways. For example, this would be a precipitation reaction because this would be a solid. This could be an acid-base reaction. Basically, the H plus is coming over here. Let's make that. This is a single replacement reaction. Again, also a redox reaction, also a hydrogen displacement reaction. This is a combination or synthesis. Two things make one. Again, also a redox reaction that is happening here. So, most of the time when you're asked to sort of classify reactions, I would say that, a lot of times you are given sort of direction, if you will. They'll maybe give you a list of ones to choose from, and you probably want to choose the sort of most appropriate, I guess, off of the list. If you just have really no direction in terms of that, it just tells you to classify it. And as you can see, even here in this question, you could have multiple classifications of the same reaction. Any questions on different types of reactions, oxidation numbers, how to classify things? Any questions on any of that there? Okay. So we're now going to switch into the next lecture notes, which is the ones It does sort of cover a variety of different sort of chapters, but it's going to cover, we're going to talk about stoichiometry, using equations and balanced equations and grams and moles to do calculations, obviously from equations. We'll also talk about molarity and concentration units, so things like molarity, mass percent. We'll also talk about titrations here. So this is now sort of a new handout that's up there as well on Canvas, so we're transitioning into that. So since we don't have a lot of time left, let's just kind of talk a little bit overview again of sort of stoichiometry. And obviously we'll get more into it next time, I think. But just to remind you sort of about stoichiometry, some things that you might obviously be familiar with. When we do stoichiometry, it really involves a balanced equation. So that's always really the most important thing when you're doing stoichiometry, is to make sure that you always are starting with a balanced equation, because if you're not starting with a balanced equation, then definitely all your calculations are pretty much going to be bad and they're going to be off and stuff like that. So for example, just take like formation of water here. We would want to make sure that we obviously have all the proper coefficients happening there in our equation and make sure that they are balanced. So what really is stoichiometry? Well, sometimes people get really freaked out about stoichiometry and they think it's like, you know, maybe super hard or difficult and stuff like that. But really, stoichiometry is really nothing more than really a conversion factor. And the difference is sort of where we get the conversion factor from. So normally when we need some type of conversion factor, you know, we open up a table and we go, okay, there's like 12 inches in a foot. There's, you know, 2.54 centimeters in an inch. You know, we go to a table, we find those things. What is different about stoichiometry is we're really using the equation to provide the conversion factor. And that's because in most stoichiometry problems, what we're given is information about one thing in the equation, but we're really not interested in that guy. We're interested in something else in the equation. So we need a way to go from, say, maybe a reactant to a product, or if we're given information about a product, maybe we need to go from a product to a reactant, or maybe we just need to go from reactant to reactant or product to product. So because there's not like a universal table where you could open and go stoichiometry sort of conversion factors, we go to sort of the equation to do that. What do we use to do that? Well, we use what is sometimes referred to as the mole to mole relationship from the equation. So before we get into the mole to mole relationship, that brings up another important thing that we talked about, which is how do we get to moles, right? So a reminder that in a lot of cases, we start with grams, and if we need to go to moles, or by the way, backwards, right? The conversion factor that we use to do that conversion from grams to moles or moles to grams is actually the molar mass from the periodic table. Right? So when we pull off that molar mass from the periodic table, that's basically how many grams there are per mole. So one of the very early steps that you do usually in the stoichiometry problem is that you convert grams into moles. So that's a very common sort of calculation that we need to do. So a reminder, periodic table, we use this really as a conversion factor to do that. Obviously, if we're starting with grams, we're going to divide by the molar mass to get moles, as the grams would cancel. If we had moles and we wanted grams, we would multiply by the molar mass, and that would get us grams. So how does that relate to the mole to mole relationship? Well, stoichiometry is really just those balanced coefficients that we have in the equation, which is why it's really important that always start with a balanced equation. From this one equation here, we could come up with several different stoichiometric relationships or qualities they're called. We could say for every 2 moles of H2 that I throw in there, I also need to throw in there 1 mole of O2. Where does that come from? It's the actual coefficients here, right? No calculation, just from the balanced equation. I also see that for every 2 moles of H2 that I toss in that equation, I get out 2 moles of H2O. I also see for every 1 mole of O2 I toss in there, I get out 2 moles of H2O. These are what are referred to as equalities. Clearly, in this case, they are not equality in terms of numbers, because clearly 2 does not equal 1, or 1 does not equal 2. They are equalities in terms of sort of ratios of what you need to throw into this reaction to actually make products. You know, kind of like when you make cookies, you got to throw a certain amount of flour in there, right? A certain amount of butter, a certain amount of chocolate chips, hopefully, or whatever else you're tossing into your cookies. So you got to throw this right ratio, right, in order to produce a dozen cookies, 2 dozen cookies, 40 dozen cookies. It's been a long day, whatever it may be. But you need to throw a certain amount of ratios of those sort of ingredients in there. And that's really what this stoichiometry and these equalities are. They're really sort of the ratio of reactants to reactants or reactants to products that you need to kind of toss into this equation to really make the equation run. Because they're equalities, though, just like a normal equality of, like, you know, 12 inches is equal to 1 foot, you could write 2 conversion factors, 12 inches over 1 foot or 1 foot over 12 inches. So for each of these guys, we could write 2 conversion factors, 1 mole over O2, 2 moles of H2O, or we could flip it around and go 2 moles of H2O up on top, 1 mole of O2 on the bottom. We could do that for every single one of these. The guy right here, we could say that for every 2 moles of H2 on top, we have 2 moles of H2O, or 2 moles of H2O gives us 2 moles of H2. And for this guy here, we could write 2 moles of H2 over 1 mole of O2, or 1 mole of O2 over 2 moles of H2. Now, from this one single balanced equation, we now have 6 different conversion factors that we could use, just like 12 inches is a foot, to do some type of calculation. And that's useful, for example, if I was told, you know, you produce this much water, how much O2 did you start with? You would use the O2H2O relationship, and we could use one of these 2 conversion factors to actually do that calculation. You won't use both, but you could use one of them to do that. And we will talk about that next time, I think. Any questions on that? Okay, we'll lay it up.